I don't know if you are able to just say hi to let us know that you're here, or to introduce yourself. And Wendy is also here. Do you guys want to introduce yourselves, or? What? Okay, let us get going then. Showing, yeah, no, that's just because I am sharing my screen, which is then sharing itself, which is sharing itself, which is sharing itself. So as soon as I click on something else, you guys should be fine. Did that sorted out when I just quickly left? So now you should only see one screen. Okay, all right. Excuse me. First things first, today I will be covering direction fields, and I will be doing a few examples with you. I think let's just quickly, you should all know where to find your tutorial questions, but if you go into Blackboard, you click on tutorials, 2021 tutorials, and then here they all are in a list. I believe you see them all, like you've got the whole semester's tutorials from the beginning. But if you want, like, you just need to then find the tutorial that we're working on. Today we're working on the first type problems on direction fields, and then Richard Pila will be doing separable equations with you. So let us begin. A direction field, I'm sure you've seen, or not have seen, your lecturers will have shown you direction fields when they were teaching you. It's just a way for us to visually represent a differential equation, or a family of differential equations, should I say. So what happens is we end up taking that differential equation, evaluating it at a bunch of different points. So each of these arrows represents a point at which this direction field or this differential equation was evaluated, and then they've put in a little arrow representing the slope or the value of the derivative of the graph at this point. Is everyone clear on that? Does anybody have any questions that they'd like to ask? Anything not clear from the lectures so far? Okay, well, in that case, let us get started. So the first question, in your tutorial is the following. So you're given this differential equation, dy dx is equal to x squared minus y squared. And then they say to reproduce the given computer-generated direction field, then sketch by hand an approximate solution curve that passes through each of the indicated points, which sounds like a lot of mumbo jumbo at the moment, or something that's kind of impossible to do. I mean, it looks quite strange. But once we get going, you'll see how simple it is in that sense. Can everybody see? Oh goodness, it's blown up, quite pixelated. Actually, let me quickly pull up this one rather. So what I've done here is I've Googled online software to plot a direction field for free, and then this is the first link that comes up, and the page looks something like this. And then what you can do is you can put in your differential equation. So the first equation was x squared minus y squared, and then you can tell it what you want it to plot. So in this case, it's used, where it says t, it means x. I think it's just coding errors. But we want this plot to be from -3 to 3. So the minimum t, or the minimum x value, must be 3. The maximum t must be 3. The minimum y, I believe, is also going to be 3. Yeah, so we're plotting this essentially on a square in the plane. And then we say graph the direction field, and it's actually just reproduced this for us. Everyone with me, following me? Where is it now? There we go. Can I get a yes? Okay, cool. Sweet. Okay. Yes, so this is our direction field. This is what we are working with. So in your text, on the question, you were asked to reproduce this, and we have reproduced it. So let's take a new snip. I'm going to snip the screen. Ah, man. There we go. All right, so, and I'm going to copy it, and let's put it into Paint. Very high tech here. Yeah. So I want this one. Okay. Then what they do is, so then we have now reproduced the computer given generated sketch, blah, blah, blah. Then by hand, they want us to sketch an approximate solution curve that passes through each of the indicated points. So what that actually means is that in this direction field, you'll see that when you start to solve differential equations, you end up with constants. And depending on those constants, your differential equation shifts and sort of looks different. I'm explaining this very well. It looks different based on your different initial point values. So if, for example, the first one we are asked to plot the curve that passes through -2 and 1. So when the x value is -2, the function value is 1. So that would be this point on the graph. So our function value is -2, our x value is -2, and our function value is 1. So this is about over there. All right? Is everyone with me? So that's the point that I'm sort of working with. Now what we can do is we can use our direction field to sort of have an idea of what this curve is going to end up looking like. So what we say to ourselves is, at this point, this little arrow over here tells me that my function is sort of doing something like this. So that's what my function is doing around there. Then I follow it, and as soon as I hit another arrow, I see, okay, now it's starting to level off a bit, and then it levels off some more. And if I go along and I follow my arrows as I go, yep, I end up with a curve. And then I go from the other side. So it came from this direction, needs to hit this curve and go down and continue and continue. And then over here it starts to level off. See this question? Do you just follow any arrows in that direction? No, so you follow the arrows. When I say follow the arrows, it's the arrows that you end up, wait, where's it now? It's the arrows that you end up like colliding with, in a sense. So this arrow represents, if the function passes through this point, then the gradient of the function is going to look like this arrow, if that makes sense. So I started at this point. What if you were not given the arrows? Okay, so if you're not given the arrows, I will go through it with you now, and just hold on a second for me and I'll help you with that. So yeah, that is, you follow the arrows. Wonderful, yeah. Okay. All right. Then if we have a look at the next one, so the next point we are asked to work with is when x is 3, y is 0. So let's take a new color. We want to work when x is 3 and y is 0. So that's going to be somewhere there. And what this curve ends up looking like is, will we be given the direction field or do we have to plot it? So you may be asked to plot it in a very small section of your Cartesian plane, and you'll be given the specific points at which you must plot it. I think there was an example in one of last year's tests, so I can pull that up for you guys just now to show you. You won't be expected to reproduce something like this in a test first time around. Okay, so that's where my point is. And what then happens is over here, if I look in this general region, it looks like my function is going to be behaving sort of asymptotically. So it's going all the way up, 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 up. And if I come down, it comes and it's going in this direction. And then when it gets here, it does something like that. And it's continuing this way. So it does that sort of thing. Is everyone still with me? Yes or a no or a, oh my goodness, you've just, okay. There's someone's, yes. All of the recordings, so all of the tuts will be recorded.
Hello?
Yes?
Can you hear me?
Yes, I can hear you.
Yeah, the graph that you just drawn now, the function that you just drawn now, the last part that you drawn, I don't get why is it between the arrows?
Why is it between? So it's just an approximation. So if you would like to have it, it could have come this way. Oops, no, sorry, let's go back to the orange. So it could have come this way, then it would have gone that way. It's very much an approximation. So it doesn't really matter what your values are exactly, as long as you are following the arrows in the right direction. So I couldn't start here and then say, okay, this function goes this way, and then it comes down, and then it goes up. You have to follow the arrows and sort of stay, like wherever you start between them, you need to stay between them, if that makes sense.
Yeah, but you just mentioned about the estimation part. So if I find two arrows which are like this one, I don't know whether can I be able to show you on your graph, but the can you see on your far left
Yes.
The orange graph, on your orange graph,
Yes.
like
Yeah.
can you see those arrows? They are like somehow they split, and you just gone underneath the red graph, which is like
Yes.
between the arrows. The graph is like it's going between the arrows. So it confused me
the
there.
arrows. Okay, so the arrows are a guideline for us. What we've done is we've picked a few points, or a few lots in this case, but we've picked points on our graph and we've sort of made little marks to indicate to ourselves what the gradient of, what the derivative of this function would be, or these functions would be in this region. So in actual fact, if I evaluate my derivative at a point, let me pick a new color. If I evaluate my derivative at this particular point there, like that, then I can actually plot a new arrow that looks something like I can have another arrow there. So just because there are arrows only at these points doesn't mean that our function can only exist or be at those points. Does that clear it up? So I'm using my arrows as a guideline to show me how my function is changing over time. Does that make sense? Okay, so if you have any more questions, you're welcome to ask. Yeah, but that is the general idea. And as you do more and more examples, it will become clear as to why we are doing this. I mean, at the moment, it kind of just looks like we're drawing arrows and squiggly lines on a graph, but we are giving ourselves an idea of what type of function we should be ending up with when we solve this differential equation. maybe if I were to explain it without using the given arrows. Yes. There are infinitely many arrows. We have just chosen like arrows in the sense that I can zoom in and I would have infinitely many arrows. But I'm drawing these arrows. We have these arrows which give us an idea of what we need to be doing. So the whole idea is that the direction field is the graph with the arrows itself. So we can't really explain it without the arrows. In that case, we don't have a direction field. You could, yeah. Okay, and then MP Pathan asked, is this all we have to do for a question like this one? For this particular question, yes. I'll do another example of what you might be expected to do for a direction field question, like a example from a test. Yeah, and then, sorry, I don't think I finished speaking about the recording. So all of your tuts should be recorded, and the recording should automatically be uploaded to Blackboard by Blackboard within a few hours. So yeah, that should be a thing, or is a thing, not should be. Okay, so let us go back. We now have, let's pick a new color. So now what we have is, we have point C, which tells us that when x is 0, y is 2. So y of 0 is 2. So when x is 0, y is at 2. This point is somewhere over here. Okay. So what then happens is, in this region, if I look between those two arrows and the arrows all around here, my function seems to be heading downwards. So it's heading downwards at about that angle. Then I continue and I continue, and here it's sort of starting to level off, and it's leveling off, and then it's almost exhibiting asymptotic behavior. So it's sort of, any function in this family of functions is going to end up doing something like that eventually. Okay, and then I start from this side and I do the same thing. It should be coming from the top, and just continuing up like that. All right, and then for the last one, let's pick blue, and the last one starts at, or the point we're given is 0, 0, and then we do exactly the same thing. We follow. In this general region, it looks like my graph wants to be, going horizontally, and then it's starting to curve upwards, and then it's continuing upwards and upwards and upwards, and it's joining, like, or not, yeah, and it's doing that. Then if I follow it backwards, it's going to be coming this way, then it comes from this direction, and it's going like that. All right. So that would have been the first question. I will go through after the tutorial session and maybe put all of it, like I'll put the graphs into a Word document and then upload them onto Blackboard. But you will also have the video to be able to refer back to. All right, is everyone with me? Are there any more questions? Are there any questions regarding this? Okay, all right. Now something that I think is quite cool, which I wanted to show you guys, is, it's perfect. Okay. If we go back to this direction field plotter. So this thing is actually already done that for us. There you go. Okay. So if I go back to my direction field plotter and I grab it, I grab this direction field and it looks something like that. And I go back to these points that I was using. No, there we go. Okay. Well, there we go. And so this plotter is quite nice, is that it actually does what you would be expected to do in a test. So you can use it to check your homework solutions or your tutorial solutions. And it's quite nice to sort of verify your solution. So when x is -2, y is at about 1, and that's what our function should have looked like. So if we pull up our function, yeah, that's sort of what our function was doing. This is picked up the wrong points. So sorry, let me quickly change the bounds. Okay, that should work better. -2 and 1. And that was, I mean, that's sort of what we had going on. If we look at the next one, when y is 3, x should be 0. Is that what we had going on for the previous one? Yes, we sort of just didn't taper off as we went. We showed that it went up along here, almost vertically. If we look at the next one, when y is 0, when x is 0, y is 2. So that would be something there, no, there. And that's, yes, that's what we had. And then the last one was the point there. And that's also something that we had. Let me pull up the question. Will they always provide us with the field arrows, or will we have to draw our own? Okay, if you are, it depends on the question. So if you are asked to take the, I mean, something like this question, you will always be given. If you are asked to sketch by hand an appropriate solution curve that passes through each of the indicated points, then you'll be given a field to work with. Yes, I will do an example of what you might have to draw. So this is, I mean, if you were asked, like what we've done is a typical question that you could be given, and there are a few of them in your tutorial solutions. There are 4 of them in your tutorial solutions, in your tutorial problems. But it's not, I mean, you won't be given just, whoopsie, just this, like just the differential equation and then these points, and asked to reproduce that all of a sudden. That, I mean, if you had to sit there and draw, how many is it? I think it's like lots and lots and lots of different errors, and then you had to go in and plot the points. I mean, there's so much space for error that it becomes impossible to mark. So remember that your lecturers also don't want to give themselves too much work. 144, thank you. I can't, 400? One, I don't know. There are as many as there are, but you won't be expected to do something on this scale. I will do an example to show you what you may have to do. Okay, so the other tutorial problems you should be fine with, or not. Yeah, it's another one's plot, and they've given you the direction field, so you do a similar thing. You do a similar thing. Then for problems 5 to 10, they give you, so they say use computer software to obtain a direction field for the given differential equation. By hand sketch an approximate solution curve passing through each of the given points. That you can, I mean, you can use this, where is it? This is your computer generated, or your computer software to generate your fields. I'll also put the link to this website in the document in the document after the tutorial. Yes, so that is sort of as yeah, that's that. In terms of an example of what you could be asked to do, let me, okay, I'm quickly going to stop sharing my screen while I quickly go find an example.
Where are you?
Hello? Okay, so let me quickly grab this question. And share content. Okay, I should be back. Please let me know if you can see my screen. Yep. Okay, so this is a question from, okay, I'll redo that one. This is a question from the, this is a question from the semester test 1 of, I think it was 2019. So this is the question we were given in our semester test. So they say, given the IVP, so given the initial value problem, answer the following questions. So here is the IVP, and then they say, draw the direction field of the given differential equation for the following. Then they say, when x is equal to 0, when y is equal to 0, when at the point 1, 1, and at the point -1, -1. Okay. So what that then looks like is you would have then had to set up a pair of axes or a Cartesian plane. Well, in fact, 1 second, this is going to be easier if I'm working in Paint. Yeah, so yeah. Yeah, man. I think it's fine. Okay, so can everybody see this, or do I need to make a plan to have it more or closer together? If you can't see it, please let me know in the chat. In the chat. Okay, so this is what set up, or you would have to draw a pair of axes and a Cartesian plane. The one thing I do want to stress with you is I'm doing everything on a computer because I don't have a tablet or some kind of device to show it to you on a screen. So these questions, or to show it to you in my handwriting, these types of questions, specifically with the differential equations, you need to be working out on paper, and yeah, you need to be working out on paper. If you hand in a bunch of squiggles and typing, the lecturers aren't going to be very happy with you, so rather stick to working on paper. And if you are having a bit of trouble with your solutions, you're welcome to message the tutors and say, can you just give me a heads up, let me know if I'm doing this right, let me know if I have everything that I need to have, that kind of thing. Anyway, I digress, going back. So, draw the direction field of the given differential equation for the following: x is equal to 0, y is equal to, and so on. So, the first thing I do is I take my differential equation and I put it into my form dy dx is equal to something. So what that leaves me with is dy, let's make this black. So we'll stick with purple. Dy dx is equal to the square root of 1 plus y squared, and then I would multiply by that x on the top to remove it from the side. Okay, everyone with me? Can I get a yes or a no or a something? Yes, okay. Awesome. All right, so this is the form that I want my differential equation to be in. And then what I do is I take my points and I calculate that's the right, yeah, calculate. And I calculate the value of dy dx. So for x equal to 1, what that then gives me is that dy dx becomes the square root of 1 plus y squared x is equal to 0, x is not equal to 1. The square root of 1 plus y squared all multiplied by 0. So dy dx in this case ends up being 0 the whole way along. Okay? And what that looks like is I get that when my along the x-axis, no, not the x-axis, the y-axis. So all the way along the y-axis, my derivative is 0. So what that looks like is all the way along, I would have horizontal arrows. No, not horizontal arrows. Yes, no, it would be horizontal arrows. Because if you think of a function with a gradient of 0, it's going to be, oh, I lie. Don't believe a word I say. All the way along the y-axis, I would put in dots. So my derivatives along those points are all 0. And what that means is that my function is actually not changing at those points. Okay? Sorry, I had a momentary lapse of judgment. All right. Is everyone with me? So do you understand why it's 0? So if you think of a graph having a derivative of 0, that's sort of when a parabola has a turning point or you have a point of inflection. So your graph is actually not changing around those points. And what my little arrows or my little vectors represent is how my graph is changing. So because my graph's not changing, I use a dot. Won't be horizontally. I think, am I being blonde? Gradient to 0, yeah. So the gradient to 0, is it a horizontal line? Can I just get some? I think it's horizontal. Okay. Yeah, it might. Horizontal. Okay. Sorry. Apparently I was right. Trust your gut. You learn something new every day. So these, my apologies again, should all be horizontal lines. So all the way along the y-axis, we have horizontal lines. And because we weren't told put them in at every half a point or every quarter point, you can choose where you want to put them in. If you put horizontal lines at every unit, then you kind of get the idea that the point you're trying to make will get across. So all the way along like that. How must we know to draw these lines on y is equal to 0? So this is the line x is equal to 0. So that the y-axis is the line x is equal to 0. So this the point, not the point, the line we're given. The line x is equal to 0 is the vertical axis. So that's how I need to draw it along here. And then I just chose a bunch of points all the way along this line to draw it at. So for the next one, let's pick a new color. Then I'm told that when y is equal to 0, what do I get? I get that dy dx is equal to the square root of 1 plus 0 squared. So this is all going to become the square root of 1 multiplied by x. So that is when dy dx is equal to x. So all the way along the line y equal to 0, so all the way along my x-axis, I'm going to have that dy dx is equal to x. So what does that look like for me? What it means is that, let me grab a pen. So when x is equal to 0, then I have my horizontal line again. Dy dx is equal to 0. When x is equal to 1, I have dy dx is equal to 1. So what that looks like is a line through like or an arrow through like that. And then when dy dx is equal to 2, then it's a bit of a steeper arrow. Sorry. So it's steeper arrow. It does look steeper. It's steeper. So basically what's happening is my arrows are getting steeper and steeper. Doesn't look like it, but you would be able to get your point across on a piece of paper. So lines get steeper. All right, and if I go along the negative x-axis, the same thing happens, but instead my lines are going to be pointing downwards. So that we're going to be getting steeper and steeper and steeper like that. I agree. Okay, awesome. So yeah, that's what you would do for this one. Okay. Does everyone see how I sort of got to where I was going? Yeah. Then for the next one, let me check the questions. Yes, cool. How many people are still with us? 39. Okay. So the next one, what then happens is, let's choose another different color. Is I'm looking at the point 1, 1. So when x is equal to 1 and y is equal to 1, what does y of 0 equals to 1 tell us? Y of 0 and 1. This point here. So this is the point y is equal to, x is equal to 0, y is equal to 1. So that then tells me that any function passing through this point, so if I take this differential equation, the function that this differential equation represents would not be changing at the point 1. So it would be, we'd either have a point of inflection or a turning point, or yeah, that's what we have. Does that answer your question? Yes. Okay, awesome. All right, so coming back here. So when x is equal to 1 and y is equal to 1, we get dy dx is equal to the square root of 1 plus 1. So that's going to give me the square root of 2, and that's going to be multiplied by 1. So this, there's my mouse now, ends up being the square root of 1. Or no, sorry, voila. This ends up being the square root of 2. So then what happens is, now I'm only working with a point. So previously I was working with lines, and they were pretty easy lines to work with, and I ended up with a nice gradient or a nice derivative at those points. Now I've only got one, and it's not a very nice one. So the square root of 2 is approximately 1.41. So that means at the point 1, 1, my derivative is going to be, approximately 1.141, and I just draw in an arrow to represent that. So in reality, this arrow would end up being a bit steeper than the arrow at 1, and no, yes, but steeper than the arrow at 1 and a bit less steep than the arrow at 2. Okay, am I making some sense? Yes, awesome. So we only draw one arrow. Yes, because we were told to draw the direction field of the given differential equation for the following. So for the line x is equal to 0, that gave us these lines. For the line y is equal to 0, that gave us those arrows. Then this is only a point. This is the point 1, 1. So then we only have to draw the single arrow representing the derivative at that specific point. Okay, all right, then for the next one, or the last one in this case, what happens is we get the following. So we get dy dx is equal to the square root of, let me open this up. Yep. 1 second. So dy dx is equal to the square root of, we're going to get 1 minus 1 squared. So that's again going to give me 1 plus 1. So that's going to give me, sorry, yes, 1 plus minus 1 squared, which is going to give me the square root of 2. And this is going to be multiplied by minus 1. So this is going to give me negative square root 2. And what that translates to on my picture or in my direction field graph is the following. A line at the point 1, 1 that looks like that. So it's a bit steeper than this line, but a bit less steep than that line. Could I please re-explain 1 and 2? Of course. Okay. Each value of x on the x-axis tells us the value of the gradient since dy dx is equal to x. 100%, yes. Okay. So yes, 1 and 2. So what I'm doing is I'm taking this line, so this x is equal to 0 represents the y-axis. That is where x is equal to 0. I haven't been given any restrictions on y. I'm just told that x is equal to 0. That is the y-axis, okay? And then I'm asked to draw the direction field of the given differential equation for or along the y-axis. Yes, if it was positive square root 2, the arrow would face upwards. So here in this case, it was positive square root 2, it faced upwards. If it was negative, it's negative square root 2, and it faces downwards this time. So back to x is equal to 0. What I would be doing if it didn't work out nice, in this case, it works out quite nicely for us. So when we substitute in any y value, no matter what we substitute in for y, when x is equal to 0, this whole expression becomes 0. So whenever x is equal to 0, anywhere along the y-axis, the derivative of my function is going to become 0. And then in a similar way, when I look at my function along the x-axis, whenever y is equal to 0, my function value becomes my x value. Not my function value, sorry, my function gradient. So my dy dx becomes my x value. Does that help at all? Yes, okay. All right, and that is, I mean, this is the type of question, okay, and then part 2, that Richard Peter will do with you, this is a separable equation, and you'll be solving separable equations with, if I were to draw the arrow facing downwards to the right. Yeah. Okay. Again, I'm lying to you. Thank you very much. Miss M.M. Mhlanga, thank you. This one. Okay, so if I think of a line with a negative gradient, right? So that's going to look something like that. That's a negative gradient. So in this case, my line should be looking like this, my arrow. And along my x-axis, it should be the other way as well. So all the way along my x-axis, these would be pointing this way. And they would be getting steeper and steeper. I will make sure to have it correct when I upload. For I, if x is equal to 0, y is the, okay, awesome. For y less than 0 and x, yeah, southeast. Zeta, you are 100% correct. They should be pointing south, not southeast, but yeah, so southeast. Okay, are there any questions? I will leave this up.
Hello, Michaela, can you hear me?
Yes, do you want to take over?
Yes, yes, please.
Yeah. Okay. All right. So that's it from my side, guys. That is direction fields. If you're welcome to email your tutors, I believe, if you have any questions. But yeah, I will make sure to upload the stuff, the solutions to Blackboard. And now I'm going to hand over to Rachapila to do separable equations.
Okay, hello guys. Like as Michaela said, I'll be taking over to do the separable equations problem. So my name is Khetepile. Yeah, and unfortunately I won't be sharing the video because my camera has some problems. So we'll be doing some separable equations. So yeah, I hope you guys are still good. Please in the chat box, just in case if you can hear me, because I can see my network seems very low. Okay, perfect. I'll just share the questions now. Can you see my screen? Okay, guys. I have an idea because like Blackboard is I'll be touching sometime. So what if we maybe into Zoom to just take a Zoom call because there's many of us in here. Just make a Zoom call and then I will save the video and upload it on Blackboard because I know with Blackboard like it's gonna cut, especially on my side, like it's gonna be busy cutting. So I can just set up a Zoom call now, and yeah, we can go as far as you guys want on the Zoom call. Yes, at least. I'll set up a Zoom call and then share the link here so that we can continue. We can't miss the session because of Blackboard. can you please consider this as like 5 minutes break, then I'll be back. Fast, I'll be back.